In this lecture, we'll be looking at the various types of glaciers that exist on the planet today and that have existed in previous periods of glaciation. We'll also take a look at how glaciers move. We'll look at the physics behind the glacial body and its movement across a landscape. Although little is known about the number of ice ages that have impacted the planet, the last ice age, in this case the Pleistocene epoch, is something that we have learned quite a bit of information about. And it is based upon that information that we are going to take a closer look at how glaciers exist today and how they have, in a sense, transformed global climates. As your author points out, wherever glaciers have developed, they have had a significant impact on the landscape simply because moving ice grinds away almost everything in its path. Most soil is carried away and bedrock is polished, scraped, gorged, plucked, and abraded. All glaciers of any type will significantly modify landscapes. They will change the slope and the roughness or the variation in elevations that are associated with local landscapes. They will redirect or completely transform systems of drainage, and they will have a significant impact on the surfaces of landscapes, removing significant amounts of pre-glacial landscapes and depositing those same materials in other landscapes in a post-glacial environment. When we look at the worldwide expression of glacial ice, we realize that all of it currently is in a process of retreat. European alpine glaciers are in retreat. They've been melting for over the last 50 years and have lost over 50% of their ice mass since the mid to late 19th century. When we look at a glacier, what are we looking at? Well, it's a large mass of ice resting on land or floating as an ice shelf in the bodies of water that are adjacent to land surfaces. When we describe periglacial processes or landforms, we are describing any cold climate processes that are directly relatable to, in this case, a glacier being present. This would include landforms, topographic features, even the microclimates associated with a glacial body and surrounding that glacial environment. Most of the periglacial landscapes that we study in geomorphology and in the work of physical geography are generally situated along the margins of glaciers, both in the present and, of course, in the recent past. Periglacial landforms or land surfaces account for over 20% of the Earth's land surfaces today. In this lecture and in the lecture following, in this case part 2 of our look at glaciation, we'll be discussing the Earth's landform history. During cold episodes in the past, as much as 30% of the continental land was covered by ice. These ice ages were climactic time periods when global temperatures were characterized by a significant number of below freezing thermal zones occurring across the planet. Let's take a closer look at how glaciers form. Glaciers form in areas of year-round snow accumulation. These are physical areas of either high latitude or any latitude where we have pretty significant or high elevation. We relate the term snow line to be that physical point marking the lowest elevation where snow can survive year-round. And we find ideal snowline expressions in places like the Andes Mountains in South America or Mount Kilimanjaro in Africa. Generally, on equatorial mountains, the snow line exists at elevations of 16,400 feet or higher. On mid-latitude mountains, such as the European Alps, snow lines occur at lower elevations, starting at elevations of approximately 8,850 feet or higher. In southern Greenland, snow lines are at their lowest elevation, occurring at an elevation of 1,970 feet. These elevations and where the snow lines are measured generally conform to what we know of the thermal zones, or what we know of thermal zones in a sense, that will result in glaciers forming. These are also ideal locations for glaciers to be studied even in our modern era. So Glaciers are going to vary with elevation and environment. There are two recognized types of glaciers, and we'll take a closer look at these. The first one I want to talk about is the alpine glacier. An alpine glacier is a glacier that is developing in a mountainous region or a mountain range. They form several subtypes. One prominent subtype is referred to as a valley glacier. So a valley glacier is a type of alpine glacier. A valley glacier is a river of ice that is confined to a valley that originally was formed by stream action. In terms of the recorded length of these valley glaciers, the range today varies from 325 feet on the low end to as much as 60 miles. As a valley glacier flows downhill, the mountains, canyons, and river valleys beneath its mass are profoundly altered by its passage. Some of the debris created by this passage erosion process is transported on top of the ice, showing visually up as dark streaks or bands. This is being deposited elsewhere as a valley glacier then retreats. Most alpine glaciers are situated within a bowl-like earthly depression termed a cirque. Well, a cirque glacier is another subtype of alpine glacier. These cirques, these bowls near the kind of starting point of an alpine glacier, mark the head of a valley glacier. They also present us with another aspect of where a alpine glacier forms. Now, when several of these cirque glaciers move together or connect in some way, shape, or form, they construct this other subtype known as the valley glacier, which we just mentioned or just discussed. So cirque glaciers and valley glaciers, these are two subtypes. A third subtype is a Piedmont glacier. So when valley glaciers coalesce or come together at the base of a mountain range, they form another type or subtype of alpine glacier, as I said, a Piedmont glacier. Here we see the Malaspina Glacier in southeastern Alaska. This very beautiful landscape associated with a glacier being present along this kind of coastal edge of what is today the southeastern portion of Alaska demonstrates the striations that I was describing to you. Here we have a number of valley glaciers and cirques coming together to form this Piedmont expression. So we recognize three subtypes of alpine glaciers: the valley glacier, the cirque glacier, and this Piedmont glacier. Now let's take a look at our second major type of glacier. So we had the alpine glacier that we just talked about and its three variations, and now we have a continental glacier. A continental glacier is a continuous mass of ice. In their most extensive forms, continental glaciers are recognized as ice sheets. Most of the Earth's glacial ice exists today as a continental glacier in some way, shape, or form, blanketing nearly 80% of places like Greenland and over 90% of Antarctica. Antarctica today holds 91% of all of the glacial ice on the planet. The Antarctic and Greenland ice sheets have such enormous mass that large portions of each landmass beneath the ice are isostatically depressed, or they are physically depressed due to the great weight of this surface environment or this surface ice. Many of the post-glacial landscapes that were affected or impacted by a continental ice sheet continue to rebound even to this day. The Vastnotkukel ice cap of modern Denmark represents the first subtype of continental glacier. In this case, it's an ice cap. It completely buries an underlying landscape, generally mountainous. A second type of, or subtype of continental glacier is an ice field. Ice fields are not extensive enough to form a dome or an ice cap over a mountainous region. Instead, they extend in a characteristic, more elongated pattern in more mountainous regions. The Patagonian ice field of Argentina represents rather an ideal subtype, in this case, ice field. An ice field's ridges and peaks are visually above the buried terrain that they cover. And this ridge and peak system in geomorphology is termed nunatak. Continuous ice sheets or ice caps are drained by rapidly moving solid ice streams that form around their periphery, moving either to the sea or to lower elevations. Now we have one additional term to associate with, in this case, continental glacier, and these continuous streams of ice in lower elevations or in areas of a continental body where it is coming into contact with a marine environment. It creates a third subtype of continental glacier, and that's known as an outlet glacier. So again, frozen streams that flow from the edges of continental glacial bodies in places like Greenland and Antarctica are outlet glaciers. They flow out from an ice sheet or ice cap, but are constrained usually by some sort of mountainous valley pass or by the water itself. Now let's take a look at how a glacier moves, the internal processes that are at work, the physics of a glacial body. So a glacier, looking through this lens, is a dynamic earthly body that's moving downslope. The rate of its movement varies with its mass and the local landscape over which it flows, and which it ultimately changes. Elevation is a big part of this equation as well. The mass of a glacier is the dense ice that is formed from snow and water through a process of compaction, recrystallization, and as we will see, this budget the mass the rate of expansion of a glacial body consists for the glacial body gains and losses of its bodily matter, or its glacial ice in this case, as it expands and as it retreats. Let's take a closer look at how this process occurs or how it unfolds. We'll start with the formation of glacial ice. To understand glacial ice formation, we have to redress what ice is. Ice, in this case, is a mineral, an inorganic natural compound with a specific chemical makeup and crystalline structure. And it is a rock, a mass of one or more minerals. Ice, as you know, is frozen water, a trait that it shares with igneous rock. Snow is deposited in layers, as is the pre-lithified components of sedimentary rock. To give birth to a glacier, snow and ice are transformed under pressure and recrystallized into a kind of metamorphic rock. So there are some pretty strong analogies between all of the rock types that we've looked at in our unit on geology and glacial ice. The essential input to a glacier is snow that accumulates in a snow field. As the snow accumulation deepens in sedimentary layers, the increasing thickness results in increased weight and pressure being exerted on underlying developing ice. Rain and summer snow melt then combined, or contribute rather, water to the system. This stimulates further melting, and the meltwater seeps down into the snow field and refreezes. What we begin to see is a kind of freeze-thaw cycle throughout the glacial body. The snow that survives the summer and into the following winter begins a slow transformation into glacial ice. Air spaces among ice crystals are pressed out as ice compacts and becomes much denser. The ice then recrystallizes under this pressure. This compaction process, this recrystallization process, is where the glacial ice and snow becomes what's referred to as firn. Firn is snow of a granular texture that is transformed as snow becomes glacial ice. It's almost plasticized. Now let's talk about the glacial mass balance. Like the majority of earthly materials and the mechanisms that cumulatively drive them, glaciers, or the process of glaciation, is a kind of open system. As an open system, it has inputs of snow and outputs of ice and melt water. At its starting elevation, a glacier is fed by snowfall. This is its accumulation zone. The accumulation zone is defined by the highest extent of the glacial body on the top and the firn line at its base. The firn line is a hypothetical indicator of the point where winter snow and ice accumulation survives year-round. It is a place where glacial ice melting or wasting doesn't occur. Yet, lower toward the glacier's terminating end, there is reduction or waste in glacial material or glacial ice. Glacial waste occurs through several processes. We see it associated with the melting on the surface. We see internal melting. We see ice removal by deflation or wind action. We see the kelving of ice blocks, and we see direct evaporation with regard to the body of ice. All of these processes of loss are cumulatively referred to as ablation. Now let's talk about glacial movement. So highways of ice that flow through the accumulation of snow and ice to areas of ablation are marked by trails of transported rock and soil debris. This transported debris is termed moraines. Like any rock, ice has a quality of hardness, color, and a melting point. Its physical nature relates to its depth. It also possesses a physical flow due to the pressure of deposits from above. Deep within the glacial ice, there is a plastic quality, as I mentioned before. It's part of the nature of firn. In contrast, the glacier's upper portion is more like hard, everyday ice. A glacier's rate of flow relates to its elevation and thickness. The Earth's ice sheets range in movement from little to none to as much as 2 kilometers per year. The greatest movement within a valley glacier occurs internally, below its rigid surface. The base, or basal slip, as is the case with the surface, moves slower than the internal plastic-like ice. So when you think about a glacial body, you're almost looking at it like a sandwich. It has maybe 3 main layers to it, each moving at a different rate. Maybe some not moving at all. And when we think about which of the portions of the glacial body seems to be moving the fastest, we would cast our eyes toward the top of the sandwich. We would look at the top as having a faster rate than the bottom of the glacier, with the plastic middle of the glacier, or plasticized glacial ice in the middle of the sandwich, moving somewhere in between the two. This variation in movement in different parts of the glacial body demonstrates how systematically dynamic it is and how hard it is to, in a sense, predict where the glacier might be moving and the rate at which it may move. The other thing that you'll see here is that wherever you are in the glacial body, you have pluses and minuses with regard to accumulation and loss. These too are factors or variables in terms of this open glacial system. Take a moment to look at the diagram in this slide. Look at specific terms or phrases in the diagram and look at where potential gain and loss is recognized in terms of the hypothetical glacial body. All of this variability and the different modes of movement or different speeds of movement that are associated with each major layer of the glacial body results in some of the discernible crevices and cracks that we see when we look at the surface of an alpine or continental glacier. Finally, take a look at this image and compare it to similar images in your readings. What you will find is that some of the terms that we've already touched upon can be found and can be associated with different aspects of the glacial bodies depicted here. take a look at some of the terminology associated with the movement of a glacier, or the location of a glacier, or where a glacier is ultimately forming, such as the accumulation zone or a cirque basin. In our next lecture, we'll look at the history of glaciation and the landforms left behind by glaciers after they leave an environment.